now I get to introduce Andrew Reece, who I'm very lucky to work with at my day job where I work on Zcash. Andrew works on Zcash as well with me. Andrew is the only person. Well, okay, so I'm going to do an analogy that I heard John say once, which is there's some kind of Zen thing where you're pointing at the moon and you're trying to point at the moon, but the guy is like, yeah, you're showing me your finger. I've seen your finger before. And you're like, no, but like, it's the moon. Like the thing, it's the thing like over there. So I have lots of conversations with Andrew where like there are these extremely like meta, insightful conversations about programming and the nature of programming and patterns that show up and all of these kinds of things. And although he told me that he doesn't feel very smart about these things, I always find that these conversations for me are extremely stimulating. And I have all kinds of new ideas talking to Andrew. And so he's going to be talking about, see, I thought this was going to be like patterns in software, but it says assuming as much as possible. So, I could have been informed earlier about that. But anyway, so give it up for the very, very wise and insightful Andrew Reece.
Hello, everyone, and thank you, Sam, for that far too kind introduction. For those who don't know me, I'm Andrew Reece. I am mostly known around these circles as the creator and lead dev on Whitebox. If you're unfamiliar, the very short version is it's a debugger with a timeline, so you can track how data changes across time. The slightly longer version is that it's exploring what happens if you can generalize the features of a debugger and a profiler and a logger and a REPL. But we're not going to be talking too much about Whitebox itself. I'll be pulling a few examples from the code base just as jumping off points. My role in Whitebox, other than coding a large amount of it myself, has been managing kind of 1 to 5 contractors at different times. And as part of that, it's very useful if you can understand the entire code base. And the basic premise of this talk is finding the patterns. There you go, Sam. There are patterns in here. Finding the patterns in ways that you can write code that are friendly to both the developer and to the machine. So here we have 2 very exciting circles. We have CPUs with all of their things that they're amazing at. Well, they're very stupid, but they're very stupid very quickly, which is really helpful. They aren't so good when it comes to indirection, when it comes to branching, when it comes to looking at memory they haven't seen before very quickly. And then humans have their own set of features. And there's actually a surprising amount of crossover here. We're also not great at context switching into new places or jumping around and remembering the entire stack of things that we've been looking at. And so it seems like there should be some intersection between these for making sure that we do things that are sympathetic to the machine and also are easy for humans as developers to understand your code. Now, so far, science has not quite been able to determine whether developers are actually human, but it's close enough for the moment. We'll be looking for the places in this overlap where both humans and computers are able to understand and operate on these things quickly. We're not so much looking for complete optimization, but a default path that is straightforward, concrete, and then the CPU will, by default, be pretty good, although you can always optimize further. I want to take a brief moment to separate generalization from abstraction here. There's a lot of crossover, but I think they're different. And so I see generalization as describing the problem space with a slightly expanded vocabulary so that you can talk about more things, but you can still talk about the same thing in exactly as much detail as you could before. And so my example here would be if you had a minimum function and you can do minimum of A and B, you can generalize that to a minimum of anything in an array. You can still do a two-element array, but you can do this larger domain as well. Now, there are costs associated with generalizations, but typically they don't have this same indirection that abstractions do. So abstractions, as I tend to think about them, are kind of a layer on top of the thing that you're actually doing, where only certain variables, only certain features are allowed to bubble through. It's kind of a semi-permeable membrane between the implementation and the interface that is presented above. Okay, let's get into it. For me, lifetimes and stable pointers are an incredibly useful architectural tool. So fortunately, most of you have been to Vyacheslav's talk the other day, and you'll know how he uses arenas. My use is very similar, but I'm just going to very briefly walk through what arenas are for anyone unfamiliar. The basic version of this is that you, using some virtual alloc tricks, have what seems like an infinitely long block of bytes. And then as you want to allocate things, you allocate the first bit, and you bump the amount that you've used. You push some other thing on, so maybe you push an array, then you push a struct, then you push a string. And then at some point, you are done with those things, and you can either pop back to a previous point, like that you've seen recently. Maybe you no longer need that string anymore. You could have generated it for printf, and then you're done with it for now. Or, very usefully, you can just wipe the entire thing, and your arena is now empty and ready to be used for something else. Now, in practice, in my code base, and I think most others who use arenas, we tend to use multiple of them. And so we have many of these stacks that are operating in parallel. You can think of these stacks somewhat like a call stack, in that after you're finished with things, you can pop back. So what this means is if you're pushing onto one arena and you have your data at the end, then once you've popped back, everything after that point is invalidated, effectively. And so this presents our first problem, which is we quite often want to interleave things that happen on different lifetimes, like things that are conceptually nested, but which happen interleaved. So as well as having the hierarchy of the stack itself, there's also a conceptual hierarchy of the arenas themselves. So here we have kind of permanent app lifetime arena, and pretty much everything is conceptually underneath that. Now, one of the nice things, if you have this conceptualization, is that if an inner arena gets a pointer to something in an outer arena, it knows that its lifetime is going to the lifetime is going to extend past its own. And so if we can make sure those pointers are stable, then we can keep that pointer indefinitely until, say, our run closes. It can keep pointers into the app. The interleaving, for instance, an example of that happens inside runs. As a debugger, we get all sorts of debug info from the OS, and that includes a breakpoint. So when a breakpoint happens, the process stops, we get control, and we want to do some caching to make sure that we're only reading the same memory once within that break, for instance. And we do that caching interleaved with recording stuff that is going to be true for the entire run. So we want to save some data, save some recording, and so that will go in the run, while the stuff that only wants to stay in the, that only extends for the entire event, stays in the event cache. Okay, I think I've done that to death. Let's move on to some more interesting topics. Type mappings. Now, you're going to see some familiar things here if you were at Ryan's talk. Whenever you're designing a system, you have a large amount of choice in terms of what you determine statically at compile time in your type system and what gets determined dynamically at runtime. In an initial incarnation of Whitebox, where the primary focus was around JIT compiling small chunks of code and then debugging those, we had control over the full pipeline of compilation. And we happened to be using Clang, which generated dwarf information. So the first version of this, we were using this dwarf debug information, and that is every type of debug information, excepting line information, but that's beside the point. So types, compilation units, functions, variables, all of that is a debug information entry. And basically all of the interesting stuff happens inside this dwarf attributes list. So that's fully generic, all determined at runtime. Sorry, fully dynamic, all determined at runtime. And then on the opposite side of the spectrum, let's have a look at Clang's version of types. Yeah, so these are all subclasses of type, and what you're not seeing here is all of their subclasses, and also all of the things that they multiply inherit from. Right. So, given our experience with dwarf debug information, as we moved into doing full executable debugging, we needed to handle PDBs, and so we needed our own format that could handle both dwarf and PDB. And we decided to go with kind of somewhere in the middle in that static dynamic split. So whereas you have this many types in Clang, we have one. But then we also have one of these other main types. I'm going to focus on types mostly later on. So this will be familiar if you were here yesterday. Each type entry, each kind of conceptual type gets an entry in our type arena. So that can be structs or base types. We got enums that have an underlying type of that base type, aliases, type defs of those, arrays, pointers to type defs, qualified types, pointers to qualified types, double pointers, qualified pointers. Yeah. Yeah. As I said, if you were here at Ryan's talk, you will have seen something very similar to this. Now, unfortunately, as some of you may be aware, Ryan is no longer with us.
Make it sound like something happened.
But he would want us to go on in his absence. He's fine. He's just had to leave early. So you'll notice that all of these pointers are going in one direction. They're all kind of pointing downwards in this graph. And that is kind of towards this notion of an inner type. And that'll come up in a sec. So this is a slightly abridged version of our type struct. You can see there's kind of a general tag, name, size, this inner type thing I mentioned, and then some per type information. You'll note that the inner type is always available. And one of the things that, having been through the whole make a debugger process before, you realize is that you really want to be able to get these inner types. It's a really useful thing to be able to do. As I mentioned, we have these qualified types and enums and aliases, and sometimes, if you're presenting this to the user as a type, that's information that you want to know, and you want to be able to show that. But quite often, if you're reading data, you don't really care whether it's an S4 or an int. You just want to know how many bytes to read and how to interpret them. So we have this inner type for finding that out. You'll notice that we have this nil type at the bottom. And that is an entry into our type array that basically does nothing, but is a place for things that don't actually have an inner type to legally point. And you can see that this points back to itself, which means if you aren't sure whether something has an inner type, you can safely just read it, and you can do inner type of inner type of inner type of inner type, and you can safely access this, which just makes the code that is using all of this type information so much easier to read without having to qualify everything in conditions about whether or not there is an inner type. Now, normally I'm on the zero is initialization train, but this, of course, doesn't apply here. Because this is a pointer, not an index, we need to actually initialize this. So I was thinking about this, and I was wondering, why is this an appropriate time to be doing something other than zero is initialization? What am I giving up here? And the conclusion I came to was that our type concept is kind of an outer level struct within our program. There's an array of these, effectively, and nothing else, things will point to types, but nothing else actually contains them. Nothing else actually contains them. Now, this means that when you're initializing, if you're initializing a struct, if it's a type, you're basically doing it because you care about the type. You're only doing it for the sake of initializing a type. And so it's really not very much extra cost to do this .nil type thing. It's also the case that because we have this as an array, the array itself is zero initialized. So you have, n elements equals 0. But then, as we saw, the types of structs that are contained, like strings, kinds, those are all zero initializable. So yeah, I think this kind of containment idea is at least a partial heuristic for that ZII or nil type dichotomy. Okay, so we've got this type kind tag at the top. The normal way of doing this, default, I think, is you have an enum, and it just increments from 0, and it doesn't really mean anything. It's just an arbitrary identifier, so you can distinguish between different things. The most semantic use of this is as an index into a lookup table. So you might have some metadata like strings or sizes or something else, and you would read that with enum strings, enum b, and get b out. If you're feeling slightly spicy, you can order these in a particular pattern so that you can do simple, like pretty small evaluations to do check more than one thing at once, and group them into some pattern. The other common use for enums is as flags. So you have each bit is either you have each flag is typically one bit set at some position in the number, and it's a bit more flexible because you can have non-contiguous elements all grouped together in this kind of flag CDE, and that's pretty much entirely what it's used for, is allowing you to have all of these booleans and switch them all on and off independently. So our outer types, the pointers, the qualifiers, the structs, enums, all of that, we don't really have a huge number of them. And we're doing debug information. It's stayed pretty much the same for a long time. And I think we can assume here that it's going to remain the same for at least a while longer. I think we have about 19 different types here. And you may see where this is going. One of the things we can do is we can just turn each of those into a flag. Now, we're ignoring base types for the moment. this may look a little wasteful. We're using 1 to the 26. That's a very large number. You don't really want to be indexing with that. But we buy some stuff with it, and I think it's worth it. This only really works because we know this max bound that we've got of there's only a fairly limited number of things that we want to represent. And because we're treating these things as flags, we can group them, because it's actually quite common in debug code to segregate different code paths by various different groups of type information. So often you want to treat pointers and arrays quite similarly, sometimes arrays, pointers. We can see we've got rval and non-rval refs. Structs, unions, and classes are all types of records that you want to often, but not always, want to treat the same. Welcome to our separate B-plot. Bits are high level. In this case, we are continuing on where we left off with and or operators. Now, you are hopefully familiar with these. We saw before, we have these flags, and we get to set them. Now, the cool thing here is that we basically get to treat our the thing we're querying against as a set, and we get to query that with our kind. Now, because of the way that these work, where we only ever have kind of one additional qualifier or pointer per thing, we only ever have one bit set in this kind, if in the outer types. So we get to do a multiple lookup with a single operation. The computer is fantastic at ANDs. It has no problem with them at all. And this, ORing these things together, I mean, ORs are cheap enough as it is, but this will just get evaluated at compile time and treated as a single value. Okay, and then we have this ability to invert the bits, and we can check that our thing is not one of these things. Now, this is simple, right? But if you don't approach this through the lens of what can I achieve using flags, how can I do this in a sympathetic way, it's very easy to end up with a completely abstract set type, or just a loop over an array, which is not the end of the world. But if we can do that in a way that is incredibly concrete, incredibly simple, and easy for the computer, that seems like a complete no-brainer. All right, so we have this inner type. We have this primitive way of determining whether a type is of a particular kind. What's quite common is that we want to get through all the way, as I mentioned before, we don't care about many of these steps on the path. We just care about the innermost thing. And so a useful thing to be able to do is we can loop over our AND query. And so you end up with a very simple way. Once you're familiar with this is about as simple a loop as it gets. And we can skip through enums and qualifiers and whatnot and get our type out. And then you can do the inverse and find the first instance of something. Again, very simple loop. Okay, so I was looking through my notes, and I got to this point, and I was like, okay, who cares? Like, how is this helpful? And the important thing here is what's not here, all right? So I look back at the dwarf code, and the equivalent of this is this. Now, that's not a totally impenetrable amount of code. You could read through this and understand it. But this is basically a primitive in all of your debug operations. And so when something goes wrong, you have to now question whether this is correct. Would you prefer to be using this as the primitive or this? Okay. Now, we've done this by looping over the different pointers. An alternative we could have taken would be to basically cache these mappings early on and have this pass through alias, pass through qualifiers, except not atomic types, because those are needed for separate things. But it's unnecessarily expensive, and we can do it fairly easily with this functional mapping. Okay, we've gone inwards, as it were. But sometimes we want to go outwards. We've started with a pointer, we've got our int, but in many cases, we want to do the opposite. What is the pointer type for this value? Do we have one? If not, we can create one, but let's at least try and get the canonical version first. So, we could have done the same as here, effectively, and tried to added the pointer to the equivalent pointer type, the equivalent reference type, the equivalent volatile, all of those things. Again, it's pretty sparse. Like most of these things don't actually have outer types. Now, I was thinking of this in those terms. Think of this as a reference to the outer type. And at some point, kind of an audible click happened in my head as, well, first of all, I slapped my forehead. That might have been part of it. But if you reframe from references to mappings, it's obvious. What is the canonical map? A hash map. You can just map from type to type. And because we have stable pointers, you can easily treat those as keys and values. Again, we have another choice to make here. Do we want to have a very simple map, but one of them per kind of mapping that we want, or do we want to include that outer type kind, the kind of thing that we're looking for with a qualifier or a pointer, in the key to our map itself? And this kind of trade-off often comes up where you can choose between kind of many simple things or one slightly more complicated thing. And in this case, I chose the slightly more complicated thing, as it's only a little bit more complexity. More choices appear. How do we want to hash this thing? So you will note the explicit padding in here, because otherwise you might not get those as a value that you expect. The compiler might do anything with them. But this way, with all of the bytes filled, we could just hash variably. That's the kind of most generalized version. But we know the type of thing that we're doing. We know its fixed size. Let's make assumptions about that and benefit from it. We can do a 2-element hash and turn that into the thing that we use as the key in our map. But we know more about the platform that we're operating on. So, on 64-bit systems, specifically x86 64, what do we know about pointers? They're not actually 64-bit. Typically, they are 48-bit, occasionally 52, and I think ARM64 has some 56-bit address spaces. This basically means we have 8 bits guaranteed at the top of our pointer, given that we know our platform. And I'll point out that as a debugger, you have to know your platform, and so portability is already, it's not a cause that we can go for. So let's take advantage of this and use those top 8 bits. It seems like we may have hosed ourselves here, because we've got massive values, right? We can't just put those into 8 bits. But let me introduce you to your new best friend, okay? We've got left shifting. These are one left shifted by 20, one left shifted by 8, all of that kind of thing. And that takes us from 8 to 256. There's an operation that goes in the other way, and that is most significant bit. You will find this incredibly useful. You have to do this slightly differently on Clang and MSVC. Clang has the benefit that it will do it at compile time. You have to do some nasty, hacky tricks on MSVC to make that happen. Okay. Let's see if we can learn by testing. Anyone in the audience, what is the most significant bit here? 1, yes. Here? Yes. Here?
0.
Yes. Okay, so we're counting from the right, from the least significant bit, and the furthest thing is the most significant bit. Great. Most significant bit here?
-1? None. No, yeah, it's a failure condition.
Undefined. Yes. So this is just something to be aware of. Okay. Well, we can look back at our flags, and the way we've described it, each of these is going to be the most significant bit is at 8, 9, 10, 11, 12. Great, and that's part of the reason that I write it that way, rather than the 0xf, whatever. Cool, so we have 26 is our max value now, and any guesses for number of bits that you can represent 26 in?
5?
Correct. We're doing 1 to the 32 effectively. And so we can get our pointer, we can get our kind, and we can put these together. And I think I have written those. Oh no, those are the correct way around. Great. Cool. So we are, in this case, shifting the pointer up and putting the kind at the bottom. And this is the machine code that corresponds to that. This BSR is basically the most significant bit that we saw earlier. The compiler gets to make an extra optimization here because it knows that the value is never above, it never uses more than 5 bits, so it doesn't even have to AND here. Okay, we did it that way around. We had a choice there. We could have done it the other way around. What happens there? Yeah, it's fine, but unless you have a reason to choose otherwise, you may as well go with the nice smaller one, less instruction pressure, iCache pressure, and it also uses fewer registers. The other nice benefit of using the small value at the bottom with a pointer at the top is that if you're really pressed for bits, you may be able to take some from the alignment bits of the type of the pointer. But yeah. Okay, is this useful? Is this, how much of an impact is this really going to have? And to be honest, probably not that much, choosing one over the other. But once you know this, there is just zero effort to choose the one that's better. So you have no excuse now, okay? Welcome back to Bits a High Level. Our main thread has been preempted, and we're going to talk about bits. Okay, so you get some bitwise number, and the normal interpretation of this is to just treat them all as one value. So this is 233. But there's no reason that you can't split out different fields from this value and treat those as their own separate values. So here, because they're 4-bit, they each fit into a nibble or a 16-bit digit. Value 14 and 9 in this case. Okay, so what can we do with that if we split these numbers into multiple parts? Right. Let's start off simple. So we take a couple of bits at the bottom, and we can have 4 values with those. We might then add a 3-length axis on top of that using another 2 bits. So we have 4 by 3, and then we have this kind of rectangular array of different values. You can think of that as an x and a y axis. And then we can add a 2-length, or 1-bit dimension on our z-axis. And now we have effectively a little 3D mapping within a single number. And that's where the value at the top exists. So yeah, our friends in the array programming language world would call this kind of a rectangular mapping. It's basically what their entire data structure. Everything is in this format. Our friends in the functional world would call this a product type, and you can kind of see why here, because you're timesing 4 by 3 by 2 as the number of different possibilities that you have. And another way of thinking about this is effectively each of these different colored dimensions is a struct member. So I like this rectangular view, but there's a more general one, which is this tree. And each time you hit a bit, or each time you hit a new dimension, you can split off into however many different options that dimension has. This is occasionally useful for coming up with the shape of things, but probably not great to think about once it's in there, and you'll see why in a sec. Yeah, same position, but now in this different interpretation. And I'll say here, and I'll probably say it again, that one of the great things about bitwise numbers is that you can interpret them in multiple different ways at different times, and being able to switch between them for the same bit pattern, being able to switch between different interpretations of that from one moment to the next can actually give you quite a lot of power. So this tree version is even more general. You don't actually have to have even dimensions the whole way. You can, once you've decided on your first split, you could completely reinterpret the bits differently. So here we have, on the left, 2 by 3 by 4, and on the right is 2 by 2 by 2 by 2 by 2. I think I said too many 2s. Again, this can encode potentially more different things you'll see in a sec, but if you can avoid it, I would. Yeah. Right then. Let's bring it back to types. So we'll start with this tree view on this type question. There's different ways we could break up our space of types, of base types specifically. We're dealing with floats, dealing with unsigned and signed integers, booleans, chars, that kind of thing. And each type has kind of a general type kind, like signed or unsigned, a bool, whatever, and also a size. Now, this float and scalar thing, I happen to know is useful in some circumstances when you're interpreting the base type. And maybe you want to encode that in there so you get this information for free. But you end up with this kind of slightly lopsided tree where it doesn't fit into this neat multiple dimensions thing that we mentioned earlier. Another thing I'll point out here is that we have an outlier case. That is F10, an 80-bit x87 FPU float. And whenever you try and map a space, whenever you try and generalize a model, well, you will often come across situations where, there's an exception. And again, at that point, you have a choice. Do you want to generalize your model so that you can account for this, or do you want to keep the model nice and simple and then keep the exception for the unusual case? and you can keep that in the interpretation of the data, kind of with the tree style thing we saw before. You can treat that. You can do that in the code. With whenever you're dealing with stuff, you just have an extra if it's an 80-bit float. Yeah, you have that choice. Now, I guess I probably should have mentioned before, the convention we have in the code base is that unless bits are specifically otherwise required, types are normally specified in terms of their byte size, not their bit size. Yeah. And again, we've got this nil type. And there's only really one nil type. And each of these kind of bottom layers on the tree has 4 values. And that means we're over-specifying nil. Well, you can either interpret it as there's a 1-byte nil, a 2-byte nil, a 4-byte nil, and an 8-byte nil, or you can interpret that as there's a 1-byte nil, and then there are 3 holes in our space. Now, for a certain interpretation, that's a problem. But if you are willing to ignore it, then you get a lot of utility from that. This is another breakdown of that tree. I know I'm missing unsigned char and various other things here, but let's go with this as a simple version for the sake of the talk. We're just kind of accepting that we have holes where all of our nils are, and in practical use, we don't really have 8-bit or 16-bit floats that we have to deal with. Although, just by having this type system, we now handle that, even if unintentionally. Okay, so I mentioned it's useful to be able to think of this as a clean separation of dimensions, and rather than as the tree. If you're thinking of it as the tree, what typically happens is you have to do each decision point in the tree as a separate conditional. So not only are you nesting a bunch more, you're kind of adding this layer of indirection in your code, you just end up with n times m different, for however many dimensions you have, different cases you have to handle. And quite often, if you have neat dimensions, you can take the value on one dimension, handle that, take the value on the other dimension, and handle that as separate cases, and end up with n plus m cases instead. Okay. Right, back to how this works in the code base. So we have our types arena as a top-level debug information struct, or debug information type. It ends up being useful basically having an entire array just for types. So we have our base types at the bottom. We've got, I should have mentioned, we have basically end up with 4 bits for the kind and then 4 bits for the size. So we have 256 different locations here. We then have some other built-in types, which we know we're going to need, but don't really fit neatly into this. So that includes things like the XMM type and the Windows thread execution block type, that kind of thing. And then we just have everything after that. It's pretty much completely arbitrary. We have our pointers, our qualifiers, all of that in there. Okay, so we have our different components of our values. We have our kind and we have our size. The fact that we have these as separate components, I mean, not only can we, given a type, determine both of these, we can then recombine them after having done some calculation and then find the new computed type. We don't have to indirect this through multiple lookup tables. It's just ORing 2 small numbers together. And this case is for integer promotion. This is a small snippet as part of that, where you have to take both kind and size into account. Okay, we have both this base type and the other outer types, the qualifiers, the pointers, and so on. Those are both within our type kind. And this is where I think it gets really cool. We do our pass-through. We get the kind of base type as part of that. the innermost type that we care about as part of that. And then we can switch on this and filter our switch to the level of detail that we care about. So we can mask off, we can basically treat all base numbers and enums as the same thing, and then they only have to deal with a single case in our switch statement, rather than dealing with, what would that be? 256, I guess, from the previous thing, different options in our lookup table. We can then deal with the different outer types as separate things. Another case, in this one, we are looking at return values on Windows, so that has a particular ABI, a particular calling convention, and in this case, we don't care about the size of the type, but we do care what kind it is, because floats get treated differently from basically everything else. And you can see, again, there's it's not no entries here, not no cases, but we don't have to deal with the entire type spectrum as if it were just a flat, undifferentiated, arbitrary number. And the last case, we can look at just the inner type, and then basically ignore all of the outer types, ignore all the qualifiers. And there's another case I didn't add here, which is where you want to read data. It's useful to know what it is, so that you can, if it's a signed variable and it's smaller than 8 bytes, you want to read it and make sure you sign extend it. And so that's a case where the full base type, rather than just one of these components, is helpful. Okay. End of part 1. Welcome to part 2, stacks and stackability, where we're going to talk about Whitebox, the workings of Whitebox that help it work more like a profiler. So again, Whitebox collects things over time, and it can collect things in multiple threads at once. This breaks down for both GUI purposes and the internal structure happen to mirror quite nicely here. So hopefully this will make sense. We have our kind of general run recording, and inside that we have run threads, and inside of that we have multiple levels on a call stack. Inside that we have all of our many calls that have happened within that call stack, and then inside that we have an individual call to a particular function. Now, a couple of things to note here. Firstly, all of these things are on, we have many levels of nesting here. And while I said we have a few arenas, we don't want an unbounded number of arenas. If we had an arena per thread, many people in here will be sane with their use of threads, but in the general case, there's really not much of a bound there, and that goes for each entry in this dimension. So we don't want to just have an arena per array. We want some other method of storing this information. The other thing I'll note here is I still want my stable pointers. They're really useful, okay? I'm going to keep them. Nothing will stop me. Right, so an alternative view on this is this. This is the kind of tree that we're forming. There are other things at each of these levels, but they're not important. I want my stable pointers to calls, okay? Or each individual call instance. What are the options we've got? Okay, I'll start basic. We just pre-allocate some array, and it's big enough, and we just use as much as we need, and we know that we're not going to need more. Works in some cases. It's not going to work here. There's too many. Each of the things is both too big and too volatile and too dynamic in how large they end up being. And that is true at each level of the stack, whether or not it was kind of directly there or indirected via pointer. Probably the default solution here would be a kind of realloc array, where you start with something fairly small, and then you double it, and you move the pointer to the new thing, and then you keep a reference to each of these things by index. You may see where I'm going here. It's not stable. And this isn't an entirely small point. So if you want to actually reference one of these things, and you're using indices at each of these levels, what are you going to end up with? 4 indices and a base pointer to start with? Like, it's both starting to get to a reasonable amount of memory if you're holding a lot of these, and also it's really inconvenient to write the code around. Okay, another option. We could indirect. We could have a meta block that points into individual chunks, and then the individual chunks can remain stable, and then we kind of reallocate this meta block structure. I think this would work. There's no kind of inherent problem with this. You end up still doing the leaking, although now at some fixed size, some constant size smaller than the full problem. And then you either leak this, or you have some pool structure that ends up dealing with all this. And if you do that, then you end up having to free things because they're not in the right place in the arena stack. I can go on about that, but I don't know. It's not great. There's also 2 jumps, so if we could avoid that, that would be nice. Common solution for variable length data where you want things to be static, where you can grow them, is this kind of chunked linked list approach. So you have 4 items on this particular case, have 4 items in each list node, have a pointer to the start and to the end. And this is great. We use this for strings, things where you work string lists, where basically all of the only thing you need to do with them is iterate through them from beginning to end. But in our particular case, a constraint that I haven't mentioned yet is that we want random access, and that is slow here. Now you may be thinking that we can just walk through and find it, and it'll be fine. Computers are fast, memory's fast, whatever. Caching has improved so much, all of that fun stuff. Maybe that would be okay with moderately sized data that you do relatively infrequently. But I don't know if you've ever seen a profiler. If you've ever seen a profiler trace, they end up being many gigabytes, and this is we do this all the time, so it's completely prohibitive for us. Another option, you could break things down in some sort of tree structure. But we said we're trying to remove indirection here as well, so if we can avoid that, that would be really nice. There's also just like so many things happening all over the place for a structure that may end up being used quite a lot. We'd like to avoid that if possible. So this is where I've ended up. We take the doubling size that we saw in the realloc case, and we took the meta block or chunk pointers approach of the case after that. And rather than doubling in place, in this particular case, we double the size of the array each time we add a new chunk. Now, there's a nuance here. I said double the size of the array and not double the size of the previous chunk. I think both can probably work, but the maths, well, for one thing, you end up with a power of 2 size if you do it this way for the total array, and that's quite nice for various things. And I think the maths works out nicely when you do it this way. So you'll see that the first 2 blocks are the same size, and then we double, and then we double again. And you may also notice that the pointers are just immediately next to the size of the array, the number of elements in the array. And that is intentional, because we're on a 64-bit system. There's only 64 times that you can double the number, including the first one, and still be representable in address space. So worst case, you end up with 64 pointers here. Okay, but what have we already said? That we're not actually in a 64-bit address space. You you can chunk that down to 48 or 52 or something around there. Okay, and then in reality, you're on an actual physical system, and you are very unlikely to have that many actual elements in RAM. Next step down, you have a real problem that you're trying to solve, and while in our first example, we poo-pooed the idea of having some known size of things that we can definitely fit all of our elements into, when you don't have to pay the actual full cost of that, you only have to pay the log 2 of the cost of that, that actually becomes a lot more feasible. And then, of course, each individual element has a size. It's not just 1 byte, typically. And then beyond that, you shrink the number of pointers you need further by the fact that your initial chunk is not just 1 element, but many, possibly decided by cache size, or page size, or some other reasonable default for your problem. There's a little bit of nuance in how you decide that. But you end up with this. It's not a completely tiny header structure, but it's completely tractable. Right. So I looked around for this. I couldn't see anyone talking about it, although I'm sure that other people have done it. Given that I couldn't find a name, I've come up with the name exponential array, or XAR, ZAR for short. So we have this kind of array idea for storing a virtual array, and but we have to actually, we need the code for this. We need to implement it. It's no longer just a single lookup. There needs to be some kind of operations to find each element. And I guess this is where I'm gonna say that abstraction and generalization are not always a bad thing. They have a cost, but sometimes that cost is worthwhile. And the way that we're going to generalize this is by treating bytes as first-class citizens. Okay. So parameters that we're looking at are the size of each element, the number of elements in the first chunk, and from that you can infer the rest of them, and the number of pointers that you're going to store to these chunks. And given that, you can basically describe this entire structure. Okay, we're going to take advantage here of another thing that we know about the platforms that we're on. In the typical Windows and Linux calling convention, if you pass a 1, 2, 4, or 8 byte struct, and there are more options for that on Linux, if you pass a struct that is exactly 8 bytes, it will get passed as a register. And so, given that we know this, it's actually not that difficult to compress all the information that we need to know into 8 bytes. So maybe it sounds like a micro-optimization, but again, it's actually the mental overhead on doing this is pretty small once you're aware of it. The other point to do with calling conventions or APIs is, we want one version of an array function is to get to the element at index I, and that's all well and good. But there are other things you want to do with them. And as soon as you have multiple different parameters that you're passing, then being able to chunk all of that meta information into one element is convenient both from a calling convention and from a developer perspective. Do you see that intersection happening? Yeah. So we have this incredibly complicated header struct, which just contains the size, because we've said that the number of chunks, number of pointers that we store may want to differ in different cases. And then, given this, we know that our chunks are going to be immediately following this, and we know that they're going to align because of the size of this thing. Given this, we can find which chunk an element is in, and then where inside that chunk it is. I'm very happy to talk people through what this is all doing. We don't really, I don't think we have time to do it currently, but you can observe that all of the operations are just shifts and addition and subtraction. It's all stuff that the computer can do very, very handily. And I think this is mostly possible because of the structure that we ended up with here, with everything being a power of 2. Now, you could have gone, maybe I want a Fibonacci structure. And maybe you could have. But if you do that, then finding that doing this inverse of the, maybe going from doing the multiplication out isn't too bad, but then going in the opposite direction becomes a lot more prohibitive. Whereas we have our best friend, most significant bit, and that does it. That does our log base 2 floored with about the latency of an integer multiplication. And depending on the platform, it's sometimes more like an addition. So it's between very good and the best it can possibly be. Okay, let's look at getting a real type that we can find. And we've introduced this with wanting to find a particular call in this tree of calls. But we'll just look at the last array in that. Okay, so I'll point out that this is not actually how I do it in my code base, because we have some macro hackery to get around having to implement this everywhere, or to rewrite this everywhere. I didn't want this talk to be too C specific, and so I'm not going to go into that, but feel free to ask me about it later. So anyway, we can specify the metadata, and then call, so we have our outer function it's fully typed, and then our inner function, it calls the generic byte-wise operator and returns a pointer to the thing it found. If this were an external function, like I said, an 8-byte struct will just get pushed into a register, or moved into a register, and then passed as one of the parameters like that. And you can actually see here we have a shift of 8, we have 30 chunks, and we have you can't see here, but it's a 24-byte element. And so at the very right, we have 8, and then 30, and then at the very end, this 0x18, that's 24 in hex. Okay, this is an external call, and in reality, particularly if you're a Unity build team, then you're actually going to get your code. Your compiler and your linker are going to know what the function is going to call, and it's going to inline them, and it's going to be happy times where you don't have to do this extra call overhead. Before we get there, I mean, we just have an awareness. We're not going to go through this in detail of the machine code that gets generated. And hopefully, you're all familiar with Godbolt at this point. Whenever you have a query about what things get turned into, Godbolt is a lovely go-to for quickly checking what things are going to look like. But this is a general case. There's nothing particularly objectionable in there. There's like, oh, there's a jump. Maybe we could have made this branchless. There's an IMUL, which is not quite as fast as some of the other bitwise arithmetic. But I mean, like, this is pretty much, this is really very good for generic code, for kind of generic operations, dynamically typed operation. And then at the end, we find out what the pointer ends up being to our thing. And so the gold standard here, which would be finding the address of an element in an array, would basically just be a single LEA, maybe with a couple of mobs before it. And while we're not quite there, if you've seen the size of some of the disassembly in many other functions, we're not too far off. Okay, so if we specialize to the specific types that we're interested in, it's actually all very similar, except there's some early outs at the top and a little trick to compute 24 times for the size, slightly faster than a generic multiply. Okay, so two things jump out at me here. One is this got inlined, the inner type didn't end up being, the fact that we did this dynamically initially didn't really matter for the resulting machine code. And the other thing that jumps out is that the dynamic version is actually not that bad. And so given that we're a debugger and we do many things dynamically, it's actually occasionally useful to use the dynamic version. And the fact that we've done it this way rather than through templates or something means that we have this option to basically have this monomorphization on the right, or a runtime version on dynamically typed version on the left. And I was thinking of this as basically byte first thinking wins over type first thinking. Okay, so why do we need this random access? Well, one of the things we need to be able to do is find elements in our calls. And here we get to make another awesome assumption. One of the great things that happens when things happen across time is that they're sorted by time. And that is incredibly useful because it means that we can binary search them. And there's many reasons you need to do this in profilers in general and in Whitebox in particular. But let's just say we need binary search. And we can take advantage of this byte-first thinking. So first of all, the default, if you were treating this in a type-first way, it would be, okay, we have our call. Let's just say we have a simple array rather than this slightly more complicated ZAR. We have our array of calls, and because we're in C, we need a separate function for each type of struct that we are going over. And we need one for calls, and we need one for stack levels, and we need one for all these other things that we've mentioned we have arrays of. And that gets unwieldy. But if you're doing a search over things, are you actually comparing the whole struct? I would say in almost all cases, no. You're just comparing some, in 99% of cases, you're comparing some simple member of that struct. Yeah, there's the occasional one where you need to compute something given multiple members, but the typical case is this. And so if you're happy you have this struct that you're looking through and you can identify a search key, you really only need one version of this function per search key type, not outer key type. Once you've gone through this and worked it out, it's not much more complicated to do it for the ZAR version. And this is the code for that. I'm not going to claim it's the best binary search. In fact, I know it's not because there are better branchless versions. But I'll just point out two things. One, we're getting the ZAR meta, and you can actually see here the case that I was referencing earlier, where you end up with multiple different parameters, and it's quite nice having your ZAR meta constrained to one thing rather than it's split out into all of its members. And the other is you just end up doing the typed get, and then get the offset into that struct, and then you know the thing that you test against, and you test, we're doing this is a binary search where rather than just finding an exact element, you find the thing that is less than or equal to that element. So it's slightly unusual. And here is where you may have seen a hole in the ZAR meta before. Here's where we get to fill that in. And if you're thinking of this as a very pure structure, maybe you're making a library for this, then I don't know, this is a member that may not make sense, but this is for our code base, this is for a specific purpose that we know. And so we can put in the things that are helpful, even if they're not pure. And so we have all of these parameters as an option. There's like the most explicit layer possible, but most of the time we don't need all of that. That's more complicated than we need, and we just binary search an array kind of as expected. Kind of general point here is I often find it helpful to have the explicit function with everything specified, and then all helper functions call that with different things. So you have this extra one layer. You don't end up then doing like this tree of specializations, like adding one more specialization for each call in that call stack. So side point though. Okay, we're gonna jump slightly to a different topic, or a different aspect of this topic. And that is mappings. Back to mappings. Now, I wanted to include in this talk a kind of full section on using the locations of things as a source of information, but it turned out there's far too much to say there, and it would completely blow out the rest of this talk. And it's far too long as it is. So we've got some mappings, and what you're probably familiar with is doing parallel arrays in the context of SOA style structures, where thing at index 0 in one array maps to thing at index 0 in some other array, and they're kind of conceptually part of the same thing, but stored separately. And the wins you get from this are maybe it's cache in that they're or the access pattern means that you're accessing all of one array and not the other one. Maybe it's a size thing where one of them only has to be bit flags and the other one is some large struct number, and the bit flag would throw off the alignment, so you end up with a bunch of wasted space. Maybe it's just, you get this mapping and you don't have to record any data. It exists in the ether for free, and you're just getting this from the fact that you have this structure. And then another case that is particularly helpful is you have two different arrays that live on different lifetimes, and they get to know about each other, but you never have to keep an explicit pointer or handle or reference or anything from one to the other, or generic map, whatever. And what that means is that the thing that you're pointing to, if that disappears, you don't have to go and fix up any pointers. You don't have to say, oh wait, no, this no longer exists. I need to make sure that I've handled that case. It just, poof, it's gone. And this shows up for us in the call stack case. Now I mentioned near the beginning that we have this kind of event cache where we look up information at the when we have a debug event, and one of the things that we store is kind of an unwound call stack. And you've also seen from the timeline view that we have this kind of profiler-like view of calls across time. And what's quite nice here is we have some parallel mapping, but there's a nuance. Call stacks, when you unwind them, you start at the current instruction pointer, the current level of the call stack. And then you do a little bit of jiggery-pokery, and you find the pointer back to the previous level of the call stack. And you end up with a kind of gnarly linked list, going from the leaf to the root. And then in our profiler-like view, we want to store that with the root at the bottom, because it means that as the size of the call stack changes, it stays in the same place. So this means that we're counting in opposite directions. And what this basically means is that we have kind of this inverse parallel case, which it's a slight extension to the parallel case, and it's, big deal, I guess. But there's something else that comes out of this, which is we're thinking about our profiler call levels, I keep saying profiler. You're getting data across this as well as calls, but I'm sure profiler is more familiar. When we're accessing data at these different levels, sometimes you're going to be, okay, at level 2, we have some data, and maybe I pass a pointer to that data into these lower functions. Maybe they modify that data. I want to keep looking at that data referenced in call stack level 2 and see how it changes across time. What you also might want to do is say, whatever's at the top of the stack, what is currently happening there? And so we need to be able to reference from both these sides. Okay, cool. This seems like a solved issue. You know, you've used Python. You've seen many things that do this. If you're kind of indexing into an array, you can use 0 or positive numbers to access from the left, or negative numbers to access from the right. And you get this 0 and -1, they're kind of the opposite sides, and then 1, -2, the opposite sides, and so on. And that's kind of in the general case, you're doing this -x + 1 with the brackets in the right place to convert from level to depth. I don't know if anyone can see where this is going. Welcome to Bits are High Level, Part 3. If you're happy to assume that you live on a 2's complement machine, which, well, I know I do, you can make that choice for yourself. Then you know that this -x + 1 is the same as a not x. Now, okay, is this swap going to make the difference between a completely amazing feature and something that doesn't work at all? Probably not. But you will notice there's many of these things, there's many operations happening on the left, and you might do -x + 1, and you're like, I forgot the parentheses, sorts of bugs. Is it x -1? What was it? What was it again? You've got to take this extra thinking step to make sure you've got that right. And it's another place that you might get things wrong. And if you know that you can do this not operation and do this flip, then that makes things so nice. It's small. It's a creature comfort, let's say. If you're thinking of negation, if you look at it on a number line, we're kind of flipping around the middle of 0. So -0 maps back to 0. The negative of the minimum number, I think, is technically undefined, but in practice often maps back to itself. And then everything else, does what you expect. 1 goes to -1, and so on. And then it's worth seeing that the not version of this, it effectively mirrors around. You can think of this either as -0.5 or the left edge of 0, depending on what makes more sense to you. And in the integer case, the second feels somewhat more appropriate. And that means that we can do level equals not depth, and depth equals not level, and everyone's happy. And, squiggly. Right. Let's have a roundup of where we've got to with this call stack situation. You may remember the tree that had run, which had members run thread, which have levels in a call stack, which have a number of calls, and then each individual call. And this is a potential layout of that within a single arena with these ZARs. So our red run thread at the left our red run at the left points to these blue run threads. The run thread, you can see the run threads are pointing to these green call stack levels, and you can see we've got 3 of them. The first 2 are the same size, and the third one is double the size. And then the stack levels, what did I get to? It calls the next one down. Sorry, not calls. It references the next level down with the chunks. And then once we're done with this, so you can see that we've interleaved pushing onto these different arrays. And if it's not obvious, the hashed bits are just memory we don't care about. Something else is there for this purpose. But yeah, we've interleaved all these things. We've done all our stuff. We've shown everything to the user. The user's so grateful to us for showing all this information, and they've fixed their bugs, and they're, oh, yes. But now it's time for another run. Let's go. Clear. You just pop back. You can zero the one array left of pointers, and so zeroing it means you have no members, and then all of your pointers are null, and it doesn't point to anything, and we reset. And it's one operation. You don't have to walk all the way up the stack. You don't have to keep all of these arrays around in some realloc tree. There we go. Part 3, pipelining dependencies. We're going to take a jump back to the debugger world here in a sec, but we're going to start with a simple example. So we're building up some case, something has happened, we want to switch, and we have our case enum A, we do the thing that happens with that, and we do some other code, and we have another case, and we get some stuff that's specific to that, and then we also get some stuff that's the same as the first one. And then we get a third case, and we've copied it again, but we're starting to think, this is going to be a little bit hard to maintain. Maybe we need to do something with this. And then we get a fourth case. We're like, yeah, we probably should do something about this. These are meaningfully the same, and this is going to be a nightmare. Like, assume this is not just 2 lines of code, but some considerable amount. So default response, I'd say, is pull this out into a function. And it kind of works. There's nothing wrong with that, and in many cases that is probably the best approach. But you will often find that a better approach is, in my particular view, is to do this pipelining thing, where you do each individual case, and then you move the common code down so that all of them end up going through that code path. And there's this extra step for setup common, because there's often something that has to be done before that. So this is the case with calls. We end up with these kind of multiple different paths. Kind of ends up as a tree. And here we have everyone's favorite data structure, the DAG. Yes, yeah. Okay, you might be thinking, like, this is an unfair example. You've explicitly said that all of these things are completely the same, and there's one of them, and they're all matching. Okay, fair point. Let's do a slightly more hard example. So now we have 5 different things that might get done as a result of our 4 different enums, and then each of our enums does a different but overlapping subset of those things. Okay. So again, kind of first version of this, pulling out in the default way to functions. You can do this, but now each of your call sites has some different context from within that enum-specific case. And also, you now have a function in your code base that might get called from somewhere else. And, either you take the approach, this might get called from somewhere else, and you handle that, in which case you have to do all of this work to make sure that you're not assuming too much context, or you don't do that, and then you later come back to this, and you're like, oh, that looks like it does the thing I wanted to do, and you use it, and you forget about all of the assumptions that you made as part of making it, and then you have a bad time debugging because there's some subtle case that you've forgotten about. So the alternative that I would propose, in not all, but some cases, is to do this pipelining approach. Okay, so in the kind of abstract, we have each individual case, and then we work out what we want to do, and then we do the things that we want to do. And that kind of ends up in this situation. Except there's there's often a wrinkle with this, which is that these have inner dependencies between them. And in this case, that's trivial. You can just order these if statements in the right way. Trivial is maybe an overstatement. Sometimes there are complexities there. But in many cases, once you've worked out what the different jobs to be done are, ordering them is straightforward. Okay, let's have a look at a couple of ways that we could do this. One is I kind of think of as a bit like you're framing what needs doing in terms of the input, in terms of the problem statement. And so using our best friend bits, yes, can we get a round of applause? We can use our linearly incrementing enum and turn that into a flag, and then compare that flag with different combinations of other flags. And again, we're doing a few operations here, but again, these are constant things that will get turned into a single value at compile time. And if you blur your eyes a little bit, this is quite similar to what we were doing with our types case, except those were already kind of pre-shifted, where we were checking against pointer and reference and array, that kind of thing, all at once. An alternative is we frame the problem in terms of what we want to do as a result, kind of the output of this event, this thing that's happened. And again, using bits, but just slightly differently, we are just specifying I want to do job 1, job 2, job 3, whatever. And then we do them. And each of these operations, bitwise ups, trivial, computer's not going to complain about them. Once you're familiar with them, incredibly concrete, kind of easy to understand what's going on. Okay, let's go one step harder. It's possible that the enum is not the only thing that determines what needs to be done. And in that case, you have this if statement at the top. And if that is true, then you kind of need to be in this output-oriented thing, as far as I'm aware, unless you start making your conditions really complex. But you're probably already doing that analysis earlier on when you're trying to understand the problem input. And it often ends up being easier to specify in this way. And then another thing that might happen is that while doing your jobs, you realize that something else needs doing afterwards. And I've written this in a slightly different way here. This is kind of doing a branch-free version of the if statement above, where you're converting some condition to 0 or 1, and then multiplying it by a flag, so that is either 0 or the flag, and then you're ORing it, which is like item potently set including, into your flags. Now, I tend to have the opinion that you can definitely go too far with branch-free code if readability is your goal. But a little bit of branch-free code will actually end up being easier to read once you're used to it, because it means you're doing this thing, then this thing, then this thing, then this thing. There's no indirection. There's no kind of extra layer of looking out into different places and trying to keep that stack of like what's happened. Your mileage may vary. Okay, we can expand this a little bit more. Sometimes just do the thing is not enough information. Sometimes you need to know, like, what am I doing with this thing? There's some parameter, effectively, that needs to be passed to the operation. And so we just add some data that's available for that. You might get to the point where you package these together into a struct. You might end up that do the thing or not do the thing is not quite the right framing. A better framing is don't do anything, or do version 1, or do version 2, or 3, or 4, or 5. And if you have just 3 options, then kind of from a bit perspective, the the flags version, 2 bits, and the the flags version, which is 2 bits, and the kind of small enum version, which is 2 bits for 3 values, are the same, but from a kind of mental modeling perspective, it may make sense to break it down this way anyway. Or you may find that keeping with just bits and having a very simple protocol there is the easier thing to understand. Once you get kind of to higher numbers, the number of values that you can represent with a few bits compared to the number of individual bit flags you can represent with the new bits grows astronomically, and so you can fit more kinds if they are mutually exclusive into a single value, and that's kind of one of the big distinctions between kind of using separate dimensions versus growing a dimension comes down to, which is kind of can these things happen at the same time, or can only one of these things be true at once? And so in this case, our job can only be beginning or ending, or it can be neither. And so this is, modulo some detail, pretty much what we're doing with debug events. This is roughly, again, skimming some stuff, what we get from the Windows operating system. We get a process has been created, a thread has been created, a module has been loaded. And you'll notice that in create process event at the top, we have this thread begins, and we have some data for the thread, what handle it is. And then also the same thing happens in create thread. And then the same thing that happens in, a module begins in load DLL, and a module begins in create process debug event. As Ryan mentioned, a module you can kind of think of as a term that encompasses both loaded EXEs and loaded DLLs. And then we have the other side of this thing, which is handling our debug event, and we get to handle the thread beginning from the create process event and the thread beginning from the debug event in one place. And I mean it's one place in the code, and that's not just like one function where it gets run, although that is true. It is also one call stack there is no call stack where this gets hit other than the one where it gets hit. So you know exactly what is happening. You know exactly the context when this is run. Again, we're handling modules getting loaded and unloaded. And then sometimes things happen. Maybe some exception got hit, and we need to break the user's process. That's kind of a job flag that we have. Okay, so a thing to notice here is that the left stuff is framed in the context of the problem. And so in this case, it's platform dependent, and it's using the granularity of states that Windows specifies, and also the way that they've split it out. And then we get to reinterpret that into a way that is convenient for us and handle that in our own code, and we can make it platform independent. And I find that there's quite often this split of like the framing that makes sense from the input and the framing that makes sense from the output, and they're not always the same thing. You get this kind of in slightly semantically compressed data formats where they represent the same information in multiple ways depending on the size of the integer. Although that doesn't actually change the way that you handle that integer after the fact. Anywho, we've got this way of dealing with dependencies. We can pipeline these things into kind of, we work out what the jobs to be done, and then we do the jobs. Great. If you look for it, the issue of dependencies appears everywhere. It's a really, really useful lens to have. If you've been following Computer Enhanced from Casey, then you'll know about the issues with dependencies at the machine code instruction level. You can think of them, in this level, you can think of them as like build system dependencies. And then you have this completely generic version, the most generalized version possible that you can think of. And then we have all of these specializations that we can apply to our actual problems that assume the things that we know about the problem space. So in our case, we only ever do the thing once, or we don't do it. You often end up in a situation where you might want to do a thing multiple times, and that's often where queues can get involved. You can have a DAG that is statically defined and then adds this element of caching, or we keep some data around from previous times, so that we not only does this thing, do we depend on the state from like just earlier in the function, we depend on previous loops of this whole iteration. And then you can get all the way to the most generic possible DAG, but who would do that? Okay. Admittedly, so this is Whitebox. This is the JIT world of Whitebox, where we basically are operating a build system, and you can see that this is not the simplest of dependency graphs. You can get more complicated, of course, but this particular dependency chain was not completely obvious a priori. We had to work this out as we went. And so having this as a more general data structure helped us to both pipe it into dot so we could actually see what the data structure was. And then also we could attach state to each of these nodes and add some more extra debug information, which is helpful. Thinking back on it, I think we probably could have gone kind of half a step more specialized, more concrete. I think that the actual operations could have been done in this, inline way where you just work out what it's doing, and your linearization is kind of statically baked in, and then you add on top of this a kind of immediate mode API for adding the debug information so that you can work out what's going on. And then that way the complexities of modeling and traversing a DAG are not in your real code, they're only in your debug code. You've simplified that into the linearized or pipeline version in the actual code. Okay, so the point about assumptions here is that you can, if you know the case you're working with, if you know the code that is running around this, if you know the problem domain, you can make so many assumptions that make it easier to understand and much faster to run. But designs change. You might be thinking, like, okay, this is good as long as my code stays exactly the same forever. But things change, and that is true. I would like to go more into this at some point, but I will touch in it now because I feel like I should. The first thing to say is you probably have some notion of what your design is going to be while you're writing it. And many programs are big, and so you write them step by step, but you have at least some notion of where you're going. There's a temptation to overly concretize kind of wherever you are, but you've got to. You just have to have that self-awareness to no, this is going to change. Don't optimize this. I don't want to tie myself into this specific limitation. And the example that jumps to mind for me on that is processes. Many debuggers will allow you to run multiple processes and analyze all of them at once. Whitebox doesn't. And so I would like to at some point, so I don't make the assumption that I have a single process, despite the fact that it's true across my entire code base. Other friends that you have are static assert, sizes, ranges, all that kind of thing. If you're assuming that your enums are in a particular range, you can check that at compile time. You don't have to pay any runtime cost for that. A fun one that I haven't seen many people do is you can just add kind of garbage tokens that are meaningful to you, make them exist somewhere, and then use them around the code where you rely on the assumption that you're talking about. And then if that assumption ever disappears, you can get rid of the, in this case, define assume foo, or you could have a constant, or there's a few different ways you could do this. And then your compiler will say, basically, this assumption is broken here, and here, and here, and here. Go and check those. I'm a fan of asserts. I'm sure you're all familiar with those. There's nothing that requires you to make those be just like simple expressions. If you're in debug mode, you can do some arbitrarily complex check that structures are all like in the right order. The things that reference each other should reference each other. Things that don't, or shouldn't, don't, and so on. I think you saw earlier, I have like unreachable and switch statements all the time, or like the end of an if-else chain if you expect it to be handled above. This is another one that I quite like, which is in debug mode, it will assert if the condition is true, but in release mode, it'll just evaluate to the expression itself. And then that means that you can like do the check for like this just shouldn't happen. I'm pretty sure that this doesn't happen. I'm not going to deal with that. Sorry, you are going to deal with that though because you're checking it. So you can be like, if this case happens that is unexpected, tell me as a developer about it, but I can do some kind of safe no-op or exit the function or pass some error code back or however you're dealing with that, regardless, and so that it's not going to affect the end user. Okay. We have been, ladies and gentlemen, preempted again by bits of high level. Okay, I'm not going to go over all of this. I'm not going to read a table off to you. I just wanted to bring up the idea that you have a bunch of these bitwise operations, right? They're as concrete as it gets on a CPU. They're pretty fundamental. They're like mathematically understood concepts and all that. But once there's often a kind of, oh, I've learned how they manipulate the bits. Now I'm done with them. But I think if you can see the other interpretations of these values, see the other interpretations of these operations, then you will find that they will apply in many cases in your code base. And just to bring one up, which I didn't really explicitly go over before, if we recall back to this is just on the topic of reinterpreting things in multiple different ways. Our base types, I know it's a long time ago now, sorry for keeping you here so long, but if you recall back, we have our base type was our kind and our size, and we have those like jammed together. And we can interpret each of those things as separate values. What I didn't say earlier, which I should have, is, okay, we've put this together. We can reinterpret those as, because we only have 4 bits for each of them, we reinterpret that as an 8-bit number. It's 256 different possible values. That is 256 different entries into our type array. And it means that we do this mapping back from the two-part type kind into a location. So like it's not just, it's sometimes one number and it's sometimes 2 numbers, and the ability to switch between them lets you do extra things. And the same goes for these operations. yeah, I'm not going to go over them. You can get the slides afterwards and look over them if you want, or you can find many other places that we'll talk about them. Okay, it's been a while. Thank you for bearing with me. Just gonna sum up some of the things. I like stable pointers. Okay, if you can keep stable pointers, things become so much easier. I know that there are cases where handles are needed, and that's fine, but there are many, many subcases where stable pointers are the best way to go. If you can break your problems down into kind of separable dimensions, then you will find that you need much less code to handle all of the cases. And like, you're a limited human being. There's only so much code you can understand. If you can fit all the things that you have going on into a smaller space, it's often going to be easier. Now, if it's not obvious with the like struct type and the product type mentions, this rectangular dimensions thing is kind of the same as a plex. It's kind of the same as a megastruct. So we are team plex, team megastruct here. So what's happening is that with your megastruct, you have all of these different members. You think of all of these as a different dimension, and at a certain point, it gets hard to visualize, but you can kind of abstractly think of it that way. And then, you don't use all of these members in every case, and those are just effectively holes in that space, as I mentioned before. Hopefully, I have convinced you that you can think of bits as high level, and you can do these operations that are kind of semantically meaningful, that are incredibly concrete, and the CPU is very happy doing them. I like pipelines. I'm going to keep it nice and simple. Try it out, see if it works for you. Again, I think that you will find that it reduces the amount of context you need to keep in your head and reduces the amount of context that needs to be, it reduces the amount that you have to add kind of wrapping of stuff to make sure that certain assumptions aren't broken, because if it's only used in one place, then you know how it's being used. Many of these cases are about kind of removing indirection in one form or another, whether that's extra calls, extra memory accesses, doing things with complicated operations where we could do them with just a simple bitwise. And the final point on generalization, I guess my take on this is you want to know. We've gone through these different topics. We've gone through kind of mappings and pipeline or dependencies, and understanding the different dimensions of things, whether that's like tree structures or whatnot, tree structures or dimension or separable dimensions. And I think that it is useful to know what the generalization of the thing you're doing is. I think the map is the really obvious example to me there, where like I'm doing a mapping, I can map. Or I can use an array index, or I can use any of these other things. So knowing what the generalization is will help you know, will provide you a way of shortcutting to what the possible options to your solutions are. And then, given your different assumptions, you can make a different specialization to do the simple thing, the simplest thing that is required that is not going to lock you in. I would tend to lean towards generalization over abstraction as a rule. You end up with many fewer code paths and less indirection and a much better understanding of what you're doing. And if you actually need to understand the code base, which you do because things are going to go wrong and you're going to need a bug fix, and if there are bugs, then your model of the world is wrong and you don't know why. So you're going to have to assume that everything is not working, and if there's more code and more indirection, that is going to be so much harder. Thank you very much for listening. I appreciate you sticking through with me there. If you want to follow me on Twitter or follow Whitebox, there's the links. Feel free to message me about this or Whitebox or anything else, and you can have a look at Whitebox on the website. Thank you very much.
Thank you so much. That was such a good talk. If you haven't already, you should go to whitebox.systems and try out Whitebox. It is truly amazing what this program can do. It is unlike anything I have ever seen before, and it's totally worth a try. So definitely go there. I did want to ask you.
That's very kind. I will just warn you that there are still sharp edges, so mind your fingers.
I wanted to ask you, I think it says it's on version 0.122. I wanted to know what the current state of Whitebox is. What's the future?
Yeah, that's actually a kind of old, that's an old version. It's actually, we just stopped doing that numbering system at some point and started saying the date that things came out because it felt somewhat ridiculous. So we're currently releasing whenever there's something new, and you know, if you bought it, you access until at least the end of version 1.0 real, which we're not at yet.
Is there something that'll mark the 1.0 release?
That's a good question. There's a number of things that we definitely need, and then there's a list of nice to haves. But I think it would take too long to iterate through that now.
So I'm in the fortunate place of having seen this talk twice now, and I think I understand it about maybe 60 to 7%. I'm getting there. So if you haven't, or in the future, once this is able to be watched as a VOD, you should definitely watch it again if you didn't understand everything, which I expect is most of the people here in the audience. But you have an amazing amount of insight. There's so many interesting, concrete details here that you've pointed out. One of the things I find very interesting is you have this sort of like empathy for the computer that helps you see the like combination between you and the computer and what is capable between you two. Specifically, like the operands for instructions can be encoded smaller if you use numbers that are not shifted up like 32 bits or whatever. And also like the whole structures that you have, basically generics in C, where with the calling conventions and knowing that you only have so many registers to pass, that sort of like three-way connection blows my mind. How did you get to the state you were able to make those kinds of connections?
So I think as a debugger, you get a head start on insight into those because you have to deal with calling conventions and you have to deal with what registers are being passed and so on. More recently, we're trying some JIT stuff in the user process, and as part of that, we've been making kind of an assembler API. So it's just function calls rather than interpreting some text, but basically doing the same thing that an assembler would for the subset of x86 that we need. And that like really drives home the encoding issues. Like this is an immediate. I have a deleted scene that where the encoding of an LEA kind of changes between you can encode. You use LEA to do these little tricks where you multiply by 1, 2, 3, 4, 5, 8, or 9, and kind of surprisingly, a multiply by 3, 5, or 9 is encoded smaller than the powers of 2, and that's like a quirk of the x86. There are reasons behind that, but like it catches you out when you look at it. So having done that really reinforced it. But I think, as I mentioned earlier, Godbolt is just like a wonderful resource. Everyone, if you haven't used Godbolt, first of all, what are you doing? And second of all, go there now and put some code in and see what happens. See what the machine is actually doing with your instructions.
So if you haven't noticed, I've gotten more than my fair share of questions in this conference. And I have around 20 questions written down here. So I'm not going to ask all of those.
You can't ask all of them. There's no way we can fit Dimitri, so we have to move into tomorrow. So you actually have...
Wait, hold on.
Yes.
How many is too many? All right. Well, for now, I will ask one more question. We'll do some audience questions. When we run out, we'll do more questions. So buckle in. So one of the things I find really interesting is that I often do, I think Casey Torres does this for bitwise operators. You'll often do like is flag set or all flag set or things like this where you kind of wrap up the bitwise operators and you kind of push them away a little bit with a define. And I think at one point you called the unary not operator a squiggly, kind of like endearingly. I'm curious, like, do you think there's a benefit to keeping those operators in the front there, like being able to see those?
Yeah, so I think this doesn't really help when you're first writing it, but the benefit of choosing one of these paths, whether you have kind of a meaningful name or the operator just bare, the value you get from having one of those consistently within a location is the ability to compare and contrast between them. So the problem is you don't know this beforehand, which of those, you don't necessarily know, you might have a heuristic, which of those is going to be useful. But you might end up with a situation where you want to contrast, like, is any bit of this set in one case and are all bits set in the other case? And I know in the white box code base we do that in a checkbox for like, is it a tick or is it the half filled in square? And in that case, the point of having these things next to each other is to juxtapose those two different versions. But then I think the raw version is useful where you end up with a bunch of these operations next to each other, and particularly if you're doing it in a branch-free way, you're just doing kind of simple maths at each point. And I mean, you saw what happened with the minus x plus 1, and you find that many of these bitwise operators have a mathematical identity with some other things. So if you have some complex combination of operators, it may actually just collapse down to 1 or 2. And I guess that's interesting from a micro-optimization point, or if it's in a hot loop. But sometimes that's also interesting from like, oh, there's some kind of more fundamental thing that is happening. I'm doing all this garbage as a way of describing this operation, or this straightforward way of describing this operation that it happens to have multiple steps. But actually, there's only one thing that's happening, or there's only a couple of things that are happening. I wish I could give a prescription to when to choose which, but it's a kind of gut feel, I guess.
You said you work with contractors. Do you feel like you ever get pushback from them being like, oh, this is scary, this is an operator I don't know, I don't use the squiggly that often, what does that do again?
I mean, I don't think we've had any issues with that because they're all intelligent and well-practiced programmers. So, I kind of think that these bitwise operators are pretty fundamental things in computing, and unless architectures change dramatically, they're going to be around for a long time. If you don't know them now, then you can learn. And they're a little bit unfamiliar at first, but I think the familiarity is the main barrier to get over. Once you understand what they do, they're fairly straightforward.
I used to have a coworker I would talk to a lot about JavaScript. He loved JavaScript, and he would often tell me that, like, oh yeah, this one-liner map thing that you can do in JavaScript, it's amazing. And I was like, well, it's a little bit hard to understand. He was like, no, you should understand map for free. That's like a thing you should know as a JavaScript developer. And the rest of it, like all these like standard library things come for free, assuming you're a good developer in this space. And I always kind of hated that idea of like just like the standard libraries, your atomic units that you should like take for granted, right? But I feel like the binary operators, as you point out here, they are more fundamentally atomic units that, like, if you understand them, and those help you out, in the long term.
Yes, definitely. And not only are they fundamental, I've kind of said this a few times, but they're very concrete. Like if you have a map over something with, I don't know, you don't know what the implementations of that are. There's maybe some side effect in terms of memory that you weren't expecting, or maybe there's some edge case that it doesn't handle, depending on what it is. And in the JavaScript case, there are a million of them. There are like, depending on how you count them, like 7, 8, 9 bitwise operators. It's something you can learn.
All right, I'm going to go ahead and open it up for audience questions. Let's go here, Yakoslav.
Okay, regarding your exponential array type, have you ever tried comparing sorting performance on, let's say, millions of items versus just regular array? Because I do those a lot, so.
No, I haven't tried comparing. We don't actually end up having to do any sorting because we're lucky enough that our input is already sorted by time.
That's an important distinction.
Yeah.
Yeah, okay.
I mean, there's maybe an edge case where like profiler style events come in that may be slightly out of order, but you're sorting like 6 elements rather than a million. You're just sorting at the very end.
Are you usually just iterating or fetching one item or?
So what happened, a relatively frequent case in the timeline, for instance, is like we don't want to show all of the things that happened before the timeline. So we will binary search at the known start of the timeline, find the first value at that point, and then iterate from there on. That's quite common. Or there are places where we have multiple binary searches happening sequentially.
No question, just admiration. Like you casually dropped a full Andrew's Hacker's Delight and the contents of a data structure white paper, and just completely cool, no emotions, not even time for people to applause. Just like, take this.
Thank you very much. That's very kind.
You need to get better at pausing for applause. Like after every slide, you should just. Any more questions?
Will you be offended if I call them Reece arrays?
I mean, no, but it's more characters. So, like, do you really want that?
Well, array, right? Or Zar.
Oh, you think just the
XAR.
RA, even shorter.
Zar Andrew now?
CZAR.
So you made a point of evangelizing for stable pointers at one point. Is there ever a time where you care about like keeping a pointer stable across multiple lifetimes, like when it's deallocated and reallocated, or does that basically always mean that you should expand the lifetime to merge both?
Do you have any particular examples in mind of when that?
I don't. I'm
Yeah.
asking if there's any case where that would be something you'd care about, or whether you'd. Yeah.
I guess the closest thing. I think we have memory that persists across between multiple lifetimes, or across multiple lifetimes, but not stable pointers to them. Let's think. I think the place where this might come up is to do with handling our run arena, because we don't want to give the memory back to Windows and then immediately ask for it again. So we want to keep that around. And I mean, so the pointer to that is from like a parent struct. So I guess in some abstract sense, there's like a run that hasn't happened yet. We're kind of between runs, and this pointer still exists. But I didn't really go into this, but you can kind of break down lifetime in multiple ways of like a value lifetime and a location lifetime and a memory lifetime. And like, so the memory is still there, and the base struct is still there, even if the thing that is conceptually referencing doesn't exist anymore. Yeah, I think that's where I come from with that.
Other questions? Yeah.
Yeah, so I find the exponential array like super cool. I've never seen it.
Thank you.
Like a mix between a slab allocator and a binary tree in a flat array. But I just want to know, like, has anyone seen it before?
I think I have seen this.
Can we?
It reminds me of like array mapped hash tries, right? Stuff like that.
Yeah, but those are now called ZARs.
No, well, those end up on trees. Those end up as a tree of nodes.
Yeah. It's like it's arrays of arrays. They're exploiting the fact that we have powers of 2 where we do logarithms and stuff like that.
Yes, but they're like log based on path length.
They
Length.
get deeper
Yeah,
as you go
yeah.
wider, right?
Yeah. So I think there's like a log structured merge tree as a thing in databases that uses a kind of similar concept of doubling sizes, but for an entire tree at a time. And that I forget the exact sequence, but that may have been an inspiration as part of this. But yeah, I'd be interested to see if anyone's seen them kind of used as intermediate data structures in code before. I will have to come and chat to you afterwards.
I think it's worth mentioning there was like probably 6 different messages in the chat and the Twitch chat being like, "Oh my gosh, this is amazing! This is our thing. Oh, what is this? This is really interesting." So it's definitely a very interesting data structure people are excited for. What do you think is the applicability for your own programs after Whitebox or other people's programs? Do you think it is a general purpose data structure for a large set, or is it like where's the boundaries there?
Of ZARs?
Yeah, like what kind of things would make it not useful, or where's the boundary?
So I obviously showed that within a single tree of types, but having introduced the idea to the code base, they've popped up everywhere. Because there's just this like effectively static header size, and then all of the blocks being pushed later into an arena, they're very easy to. You can have the header on the stack, and then have some scratch point to an arena, push types, push strings, push arrays, ZARs of any length, and then once you're done with the, and you can the important thing here is that you can interleave pushing onto multiple virtual arrays at once, and then just pop back at the end, and they're, it's as if they never existed. So keeping that main advantage of arenas, and the pitfalls of them. One of them is the same as any other. Actually, before that. So one way of thinking about them is as a generalization of regular slices, where a slice would be number and pointer, and this is just number and pointer. But the pitfall is true with kind of any chunked data structure, where you can, if you interleave pushing some stuff, and then you take another scratch point on your arena, push more things, you may add another chunk onto your ZAR or other chunked array-like thing. And then when you pop back, you now have a ZAR in a partially valid state. So you've got your first chunks and your last chunks. And so accessing this will occur legally, and accessing that might not occur every time, and so you can hit that. So that is a case to be careful of, but I think that is, as far as I can see, just unavoidable in the case of trying to have stable chunk arrays of any sort. And once you know to watch out for it, you can you can do things like, I mean, ASAN is an obvious example. You can poison the end of your arena, and so accessing it is immediately immediately shows up loudly. And then the other cost to them is you have 20 pointers or however many pointers. Now the nice thing about that is that you can, you only have to add, if you add 3 more pointers, you've octupled the size of your array. And it's pretty easy to convince yourself that that is sufficient for uses. But if you end up with a really large number of otherwise small data structures that refer to a typically small number of things, but occasionally it's large, then you end up with quite a large overhead of these pointers. And yeah, I mean, you can use one of the other options in those cases. You could move back to the general case. I think the most general thing is possibly the tree case. But there's various options that we went over that you could think through for your problem.
Yes.
So they kind of exist in reference in a blog post from the machinery guys. Rest in peace.
Well, they're gone now, so.
Yeah, but they don't end up going with them. They kind of think about them and say, nah, we'll do something else.
Yeah, I think I know the article you're referencing there, yeah.
I don't think they realized that the number of pointers you need to keep is bounded.
Yeah, I think that was an important thing, yeah. What made it worth moving, because if you have to have that extra pointer in direction, it's I don't know, is that really worth it? But the fact that it's that relatively small bound makes it quite convenient to keep, you have this single array structure all at once.
Yeah, they suggest keeping the pointers in a dynamic array. I don't think you would suggest that if you realize, oh wait, I only need this many.
Yeah.
Yeah, the thing I was thinking of is doing that too.
Cool. So it is normal.
To some extent.
Sam, how are we doing on time? Do we want to cut off at a specific time? All right. So one of the things I learned a lot from your talk, or when I originally saw it especially, was...
Keep asking.
Yeah, this idea of parameter space, and especially how you deal with holes, right? So oftentimes when I'm trying to make a system, I really want that system to be clean and kind of perfect in a way, right? So when I come across a hole where it's this combination of parameters, that's not defined. That seems weird. I must be doing something wrong. Yeah, I guess, how did you come across that concept? So you essentially advocate for the holes can be fine, actually, right? So you do this with your 10 byte float, and even though it technically is a slightly unbalanced parameter tree, it's more useful to have a consistent parameter space that you can talk about stuff with a hole or an extra thing on top.
Yes. Now, I guess the reason that I think that is because I was already on Team Megastruct. And then, I listened to some array programming people talk about what they're doing with their different dimensions and the fact that all of their arrays are rectangular, and they talk about having holes, but how it doesn't matter. The real benefit comes from having this simple and consistent mapping for things and a simple and consistent identity. And then the connection between those, I know I mentioned all these different things, and it may have seemed somewhat random to bring up array programming and functional programming, but the notion of the product type, once you're familiar with the fact that a product type, a struct is a product type, and that's just the fact that it's referencing effectively these different dimensions, then that kind of clicked in, making the link between these two things.
We'll take another audience question. Let's go.
How important is the rule that the first element of your XOR has to be 2? Because I know that means it's going to be a power of 2, yes, but what happens if you have a power of 2 minus 1 as your size? How bad is that? Does that mess up your entire get function or something?
So how important is it that it's a power of 2, or how important is it that it's exactly 2?
Size of the entire array is always, because I saw your first element is always going to be 2 elements. instead of being 1, 2, 4, you have 2, 2, 4. I know that results into an array size of like power of 2 instead of like power of 2 minus 1. And how important is that?
Okay, so they don't have to be just 2. That was just for the to keep it small on the slide. The way I have my implementation is the first is always a power of 2. Commonly like a shift of 6 or a shift of 8, so 64 or 256 elements. Now on the context or on the question of non-power of 2 base sizes, part of the answer to that is like you get some of the benefit of this non-power of 2 thing by distinguishing between the size of the element as just an any size that doesn't have to be a power of 2 anything, and the number of elements being a power of 2, because it means that you can treat indices as powers of 2, but not it doesn't have to be a power of 2 offset into the array. No, there's the problem is I think determining which chunk things are in, and if you have non-powers of 2, it becomes you have to do like a log operator or some other trick that probably I'm pretty sure there are tricks that exist in Hackers Delight for like integer logs. So you could probably use one of those if you can find one. Computers are like doing things with powers of 2, so.
It was because I had like I was just thinking about like binary searching stuff, and anyways.
Another downside with these data structures is that they're slightly awkward to take subslices of. And so the kind of naive option there is to do just like a pointer to the thing, or just copy all of the size and the pointers, and then have a begin and end offset. I did work out the implementation of a kind of general sliced version of this, where the first chunk is variably sized, and as far as I can tell, that would work, and it works in part because you have to treat 0 as a special case anyway. But in practice, I haven't used them once since implementing it. Your mileage may vary.
One of the quotes in the talk that I felt like you should pause and wait for applause. You said something to the effect of byte first thinking wins over type-based thinking. And I believe this is in the context of what I would try to describe as like C-style generics, but then you also do this parameter space packing, and then that makes the calling convention much better, and like all these things come together, right? Do you mind explaining like that quote a little bit more?
I guess one avenue you can go down with that is borrowing some complexities of the C memory model. The bytes are an actual base reality. They're there, and they have some bit pattern in them, and you can interpret that bit pattern in whatever way you'd like. The types are an artificial construct on top of that helps us think about them and helps us catch silly mistakes. And while they're useful, they're not the concrete thing that are there. And so if you can think about things like, if you can think about what's actually there, then you have a good chance of being able to work out something you can do with that.
Do we have any more questions from the audience? I have let's go, Masha.
Yeah, but it's not a real question. I'm sorry. So the very last slide you had, was marked as 100 and the third one. But it was also written that you have like 111. It's very secretary, and Conrad loved that.
Would you like to see the deleted scenes?
We would like to see the deleted scenes.
Okay. These are slightly less structured, but I guess welcome to part 5 of Bits at High Level. Okay, so first is... Thank you. I actually lost count, however many parts this is. Again, I mentioned before, common thing you want to do, find some value in a lookup table. As a debugger, we have to deal with fast fail codes, and some of these are considered fatal, some of them are not. And the straightforward thing would just be to pack these in an array of bools. And that would work, that would be fine. In fact, it's a complete non-issue. However, it's wasting 7/8 of the space, and it hurts my soul, and it's... yeah, and there are like 76 of them or something, depending on which Windows platform you run. And the trick is realizing that all of the interesting ones happen under 63, and then you can pack, rather than, it's common to think of lookup tables as memory that you look at, but you can also think of those as just values that you look at, and you can kind of pack the value into a 64-bit integer or however many bits you need. And then, okay, so you've probably seen like single-bit bit packing, but there's no reason you have to stop at 1. It's possible to pack, any number of, you have a fixed number of bits to play with, and given that, you can scale how many different elements you have and how big each of those elements are within your like literal immediate value array thing. So if we look at basic version, we have bool array of all of these different values. You can index into them and get the value out. It's pretty common. And then we have the same, but kind of shifted into this immediate mode world. And like, this is, if you haven't seen this before, this probably looks unfamiliar. But if you blur your eyes a little bit, it's quite similar to the array definition. You're shifting by the index into the array multiplied by the number of bits each value in the array takes up. And then on the, so that's creating the value you're left shifting. And then on accessing the value, you right shift it so that those bits are the ones at the bottom, and then mask them off. And you can see that there's a relationship between the number of bits, and how you shift and how you mask. And then you can look at the disassembly for that. And like I said, LEA, depending on exactly how it's being used, has slightly different encodings, and so you end up with a slightly differently sized thing. But you end up with 4 instructions that don't touch data memory. They're only touching instruction memory. And if you're thinking in terms of total memory, you end up with slightly less. Now, again, it's one of those cases where it's like, who cares? When am I going to use this? You end up with a similar total memory footprint. The case that I've found is, and maybe it's just my own like personal mental disorder, is with when you have a small array that gets, you have lots of these small arrays, and each individual one gets touched infrequently, so it won't be in cache, but you end up touching a lot of them total, then it kind of becomes worth, I don't know. If I do it this way, it gives me a peace of mind, and it won't be, the memory cache issue won't be an issue, and I don't have to think about it. That way, it haunts my dreams, even though it's 7 bytes, whatever. And then the other use for this is it's kind of I think it's a John Blow, something John Blow said at HandmadeCon. Oh, sorry, yeah, one of the early HandmadeCons about one generally preferring arithmetic-based code to like if condition-based code. And if you have the ability to think of your data in terms of these little mini arrays, then you get to do this. And the kind of furthest point that I think my use of this has got to is I have like these little teeny structs with two 2-bit members, and then I can pack two of these structs into an array of 8 bits, and then I have an array of those bytes, and then I have another array of those bytes. So this is accessing like the it's using, because it's a 2-element array, it uses a bool as an index, and then you shift it by the index times whether or not you shift it by 4, and then you add on the shift of whether you want the first element in the struct or the second element in the struct, and then shift it by that much and mask off the couple of values. I guess it helps in this case that both elements of the struct are the same size. What was this? Yeah, there was some kind of general recommendations around a little thinking about bit packing. Like, does it already, if you just put the value in some bits, does it already fit in those bits? If so, you're done. Does the maximum value minus the minimum value, does that range fit in your bits? If so, you can shift it by the minimum value and then reintroduce the minimum value on the way out. You can think of it rather than think of it as a range, you think of it as discrete values because it might be sparse, and then you can, if you have 255 different values, regardless of how different those values are, regardless of what type they are, you can refer to any of them uniquely with 8 bits. And if, so then the simple version is you'd put that in an array, but there might be some pattern that you can exploit so that you just get the value out immediately without having to touch memory, or you do the somewhat, you do the bitwise immediate array version thing, or you do some more like real compression style thing with, what is it? Arithmetic trees, I forget the precise terminology. If you want to know more about these things, Hackers Delight is quite well known. HackMem is a PDF that goes around occasionally from like at least 50 years ago, but I forget exactly when. It's a little bit more kind of it's about solving the scientific problems rather than the direct kind of more immediate use of bitwise arithmetic that Hackers Delight has. And then as an HTML with the URL with a couple more things that probably also within one of the other ones. Okay. This is like one of the earlier slides, but this was blacked out before. It's just a nice simplification that if you have flags, you can you don't have to have a separate enum for the non-shifted version of that flag to index into them, and then you can get the value, both set and get the value like directly in a way that is obvious how it relates to the original flag. And like I said, the Clang compiler will let you do this at compile time. The MSVC compiler will not, which is a shame. But this is an option if you want to do it on MSVC. another option is just to have the non-shifted values beforehand for when you're setting the compile time, like when you're setting the flag string index, and then like hidden in here is another use of this otherwise ridiculous array access. So each nibble in that, each digit is the bit, the highest bit within a nibble, and then you can. It's the other case where you would use this slightly ridiculous array indexing is in compile time stuff where you can't access arrays, like actual arrays. And if you want to walk through that, I'm happy to go through that. And then a little trick is, like I said, and as you knew, most significant bit is undefined when you get a value of 0. It's that there are reasonable ways that you can wrap that so that you get -1. I think someone mentioned as the end result. But typically, I just have it as the bare version. You quite often end up in a situation, like in my earlier code, where the first thing and the second thing, like the 0th thing and the first thing, are handled in the same way. And if that is the case, then you can do this like X or 1 trick. And so if it was 0, then it becomes 1, and then the most significant bit is 0. If it was 1 already, then it stays the same. And if it was a higher bit was set, then this is a no-op, and you just still get the high bit set. I think that is all of the deleted scenes. Yeah, there you go.
Another round of applause. Do you have a limit of how many questions you want? This is an easy one, actually. Do you think using something like Arc would go a long way or help you in any way? I believe that Whitebox is currently using DRIM GUI, but I'm curious. Specifically the immediate mode UI Arc UI.
That arc of the many arcs, yeah. So I caught some of that on stream, but I was not here because I have a problem with my cache eviction strategy in my head, and so if I'd come to the talks earlier, then I wouldn't have been able to remember anything for these for my own. So I have glimpsed it, but not seen the details. It's very possible. I'm kind of using DRM GUI in a way that it's not really intended to be used, and it causes some friction, and it at some point does need a new UI.
Are there particular like wish list things you want from DRM GUI, or if you were to use another framework, you would like something that does X?
Part of the problem is that it's not set up directly for exactly how I want to do profiler and debugger like views, which would be unreasonable to ask of someone's UI, which kind of implies that we should probably build our own. But that's a sort of rabbit hole. Yeah, I think a lot of the issues come around with when we want to build custom UI features.
Are there any more audience questions?
This might be a bit of a big question, but we were talking earlier about hash tables and how you had a sort of new way of doing that on top of arenas. Would you want to expand a bit on that now?
This was a discussion we were having outside of this talk. Yeah. So, okay, hash tables. You have. By the way, if anyone hasn't implemented a hash table, I would recommend going and doing it. Not necessarily for use, but to understand the different things that are going on there. It really helps take something that is normally consider magic because of a lot of the hash magic that's going on and turning that into something that's concrete. But specifically to the question, okay, so first thought is many of our uses of hash maps are as acceleration structures, kind of pointing into already stable places, and so I'm far less concerned with having acceleration structures be stable than having the kind of quote unquote real data be stable. But that's not all cases, and you do want, as I said, it's nice having stable things. So you have a few options, and as I mentioned to you before, to my shame, many of the the general hash table that we use within Whitebox is still using realloc, because I did it ages ago, long before coming to the aesthetic sensibilities that I have now, and basically it's just never been a priority to change. Okay, I'll stop deferring and answer the actual question. So we have when you implement a hash table, you have your you hash your key, and then you end up with a thing that you turn into an index into some other array, and then from that you either directly have the keys and values in there, or you have a way of determining what the keys and values are. And I guess the first way of explaining how you could keep that stable would just be to slap it onto a ZAR, and rather than the index being a direct kind of modulo offset into that, it's kind of like a virtualized, it's just the regular index put into the ZAR. The difficulty then comes from when you grow the array, you need to rehash things. But okay, as we've all learned, right? Powers of 2 are loved by computers, and so they're loved by you, yes? So we have all of our hash blocks are powers of 2, which means that an index into that is using an exact number of bits. And so when we grow our hash table, and by what power do we grow our hash table? We double it, yes. Excuse me. When we double the size of our hash table, we now have effectively 1 extra bit at the beginning of our index. And so the possible solution that we were discussing for a linear probing hash table is that you can scan from the beginning of your block, and then each time you hit something, you know whether or not there's only 2 options. It's either going to stay where it is, asterisk, or go to the equivalent, like the same offset, but in the other second chunk of the next chunk across. Okay, that asterisk is to do with collisions, as it always is with hash tables. And yeah, I mean, there's some implementation details you work out. That having not implemented it, it seems like you could effectively remove an element each time you move it, and then everything else would shift back into place. And if you removed it, you don't move forward, you just look at the same place again until you've gone all the way through. There might be a slightly smarter way of doing it that skips some of that work, but I don't have any confident statements on that. And then the other way is to do, I think you mentioned with the like hash array map tree, where then all of the nodes are, you have a bunch of nodes where your base data is stable, and then actually your intermediate nodes are stable as well. But you have your log n accesses into the various endpoints, and I think that's how like C++'s ordered map or unordered map works, which I don't know why I know, because, well, I don't have to deal with it, so yeah. Yeah. The other thing you could do is, yeah. So you have more options that you can, if you keep you don't have to have the same structure for your slots, your bucket pointers as your actual key value data. So you could have your key value data in whatever storage you like. Like if you don't need to iterate it, you can just put it wherever in the arena. Or you can do like trunk linked lists or one of those other collection structures. And then your slots can go, you can either just leak the old ones each time and double, or you can have like power of 2 pools within your arena and free it from one that goes on the free list for like size 8, and then you have a new one of size 16. Well, you do that after copying the things over, after rehashing the things over. Yeah, I think there were some other options, but they have slipped my mind.
All right, this will be my last question. How much of this talk do you think applies to C or C++, and how much of it applies to all languages? In other words, can I tell my JavaScript friend that he should watch this talk and follow the advice?
So first of all, I mean, the slightly glib answer is that if you're doing things like the treating your value as a very small, like 32 element set or other things like that, then you do still get that win of it becoming one operation rather than a loop of operations or some other more complex system of operations. But yeah, so the other side of it is like C, C++, other systems programming languages, you're running on an actual computer and they have these instructions baked in as like fundamental operations. And while I think most scripting languages have them, you're kind of still going through all of the indirection of any other operator, and a lot of the, like previously we kind of compared the latency of an imul to an add, and I'm pretty sure that the speed difference between those two instructions is completely dominated by the VM on other languages. Although I guess, having said that, like V8 is pretty impressive at turning things into machine code if you can structure your data in a way that it can know to JIT the machine code and not do the generic VM thing.
Yeah, I imagine there's still quite a bit of compile time analysis and optimizations and whatnot that can apply.
But there's, I don't know, maybe this is just because I don't really live in that world, but there's a lot of black box magic in the V8 compiler. And I know there's magic in regular compilers, kind of, but the kinds of changes that you're going to get are kind of. No, I'm gonna say they're more predictable, but that's going to open up a whole kind of worms. That's a bad idea.
I think that we'll call it there. Thank you so much. Another round of applause for Andrew Reece.